Hi, everyone. Welcome. Great that you're here. So yes, let's start with this adventure in distributed programming. So I'm Martin. You might also have seen me online using the handle QQWY. Within Elixir, maybe you're using my handful of Elixir libraries that I'm maintaining. But more probably you've seen me on the Elixir Forum, where I'm a long-time member and one of the moderators. So I've been doing software development now for more than half of my life professionally. And one of the things I like working with the most is very complex systems, such as distributed and decentralized applications. And this is also one of the things that I really looked forward to when starting working with Elixir for the first time. Now, 9 months ago, roughly, last summer, my company Resilia started with our first real project running distributed Elixir. And this talk today is a little bit about this project that we've started and experiences we've had with running distributed Elixir for the first time. So this project is called Planga. And Planga is a seamless instant chat integration to add to your existing web application the capability of users to chat with other users. And before Planga existed, you either had to include some third-party service where people had to log in with, for instance, their Facebook account, which is not nice because you already have user sessions in your app, or you had to implement something yourself. But properly implementing a chatting system is not trivial to do, especially if you're not using the right technology stack. So Planga handles the chat part of your application so you can focus on your main business core functionality. Now, Planga is both available as a software as a service, as well as a free version that's open source, and you can take it from GitHub and run and host it yourself. And the main goals that we've had from the start with Planga is to create something that's very simple to use in whatever technology stack you're actually having. So whatever type of web app you're building, as well as creating a system that is really stable to show people what is actually possible if a chatting system is implemented properly. So that meant that we had to deal with all the nitty-gritty details of creating a chatting system with all kinds of stateful connections. But luckily, we decided to program this using Elixir. And Elixir's processes and also Phoenix's channels to communicate with the browser really made this a lot nicer. And then we wanted to make the second promise true, where we wanted to make it as stable and as fault-tolerant as possible. So we just spun up a couple of extra Elixir nodes and configured every one of them with the same Erlang cookie, and then stored data in the distributed Amnesia database, and all was well, and everyone lived happily ever after with our distributed application. Or so I would like to say. However, we tried to finish a proper production distributed system before this conference. And we're almost there, but it's not entirely finished because running a production cluster is slightly harder than the getting started hello distributed world examples might make you believe. And the main reason for this is that, and this is also was already pointed out by Michael Muscala during the CodeBeam Light in Berlin in 2018 talk about FireNest, that there's a lot of information and great tooling for running Elixir on a single computer. And also there exist some wonderful tools in Elixir and Erlang to run a huge cluster of nodes, so a huge distributed system. But these tools usually expect you to already have a dedicated team of people that intimately understand every detail and are able to configure everything specially for your needs. And actually figuring out which parts of this configuration also make sense for a smaller cluster is very difficult, and tooling for these smaller clusters is still more limited. So much of the last 9 months has been spent with learning about the different tools that exist and what type of tools and settings not only make sense for a large cluster, but also for a smaller one. So that is part of what I want to share with you today. And besides this, I also want to give you a foundation or an overview of distributed programming in general, and tell you some of the lessons we've learned at Planga, the easy way, as well as the lessons we had to learn the hard way. Now, this is the first real distributed Elixir project of me and my coworkers, which means that probably some of the things we're doing is also not perfect. And I know that there are some people that are even more experts on this than I am in this room, probably. Also, the talk after this one is, I believe, going into a more practical aspect of distributed programming Elixir with deploying it to a cluster. And also, there's a great masterclass on Wednesday from 9 to 5 that can go into much more detail than I'm able to in these 40 minutes. So there are 4 things I basically want to cover. I want to give you a foundation, a crash course introduction to distributed programming in general, and then touch on the different tools within Erlang and Elixir that make it easier in these languages. After that, I will compare a couple of different distributed databases, as well as explain why it might make sense to separate your database cluster from your main application cluster. And finally, I want to tell you about some of the decisions we've made at Planga and where we see us in the near future. So now, with all that being said, let's dive right in. So what is a distributed system in the most simple case? It is a piece of software that not runs on one computer, but on 2 or more computers at once. And there are 2 main reasons to do this. One is that 2 computers can do more work in the same amount of time. And the other is that when one computer breaks, hopefully the other computers in the system can still perform some useful task in the time that it takes to replace it. However, because these computers have to collaborate together, they need to communicate, and this is difficult. I mean, humans collaborating together is already difficult, let alone humans telling computers how they should coordinate and communicate. And why this is the case in general is also something I want to touch on. Maybe you've already seen this at the very start of my presentation. These are 8 rules known as the fallacies of distributed programming, and these are things that are not true. However, usually we take them for granted when writing software for a single computer, because usually we don't have to care about the laws of physics, about the speed of things all the time, like latency and the reliability of the network, because we're on a single machine. But these rules suddenly become really important once we're talking about multiple computers. In general, there is no such thing as free lunch. Not in computing in general, but even more so in distributed computing, because almost all decisions you make will have a trade-off somewhere else. And if you think, well, is this a good thing to do? Then the answer is almost always, it depends. And the most basic example of this is given by the Byzantine generals problem. So say we have 2 generals, and they want to coordinate together. So these are 2 nodes that run in our distributed cluster. And the first general sends a message to the other saying, hey, we should attack right now, so they can coordinate their efforts. And the second general now considers this for a moment and stores that it has seen this message and sends back an acknowledgement. Now both generals are aware that they both have seen the same information. Wonderful. However, this can go wrong in exactly 3 ways. Either the message is not properly sent, or it's not properly saved once it was received, or the acknowledgement disappears on the way back. And all these 3 cases look exactly the same from the point of view from our first general. And that is a big problem, because in some of these cases, the second general has seen the message, and in some of the cases, he has not. So what should the general now do? In this case, should he cancel the attack and wait until the other general sees it again? But this means missing a nice attack opportunity. Or should he proceed, but risk an uncoordinated attack because the other general is not aware of his efforts right now? And this is a really difficult problem. So the fact that the situation occurs is given by the Byzantine general's theorem, or problem. However, these choices that you need to make, and that these are the 2 choices you have, is what is given by what is known as the cap theorem. So in a more general sense, when there's some operation we want to perform, some data we want to store or work with, but we cannot reach another node. Do we cancel the operation, which means we cannot currently do something right now? Or do we proceed, but therefore risk inconsistency because the other node is not aware about what is happening? This is usually given by CAP. You can at most pick two, so consistency, availability, or partition tolerance. And often it is represented by this Venn diagram. However, this diagram is slightly confusing because picking CA means that you don't care, you close your eyes to the possibility of ever having a partition. However, in our physical world, with its physical laws, this is not true. And when you run your system for a longer period of time, when more requests happen, at some point, this situation will occur. So a better way to look at this picture is like this. So, consistency over availability or availability over consistency. Which one do we want to pick? And this is a really difficult choice because it depends on what kind of data you have in your application. CP really makes sense for critical data. And the nice thing is that you will never have to fix state. So it's a lot easier to work with because you don't have to think about this. However, it needs more communication, which means that it's harder to scale and harder to have high throughput of the system. On the other hand, an AP system, while easier to scale, needs to be able to reconcile the work that happened during a partition, which might result in conflicts. And this is a very difficult problem to solve. So looking at a bit more detail, CP systems usually use a form of two-phase commit and other similar, slightly more complicated procedures to do the same thing are known as Paxos and Raft. And these can be viewed from a very high, simple view as voting systems, where all nodes are together in a virtual room, deciding on what information will go into their storage in their memory in which order. But this means that while you will always have a nice consistent state, you will have to wait until more than half of the nodes is available before you can store anything. One main example where this is used are many of the different SQL-like databases that allow you to run them in a distributed way, such as distributed Postgres, and also MongoDB nowadays, and FaunaDB, Bigtable, vault-DB, or other examples that try to do the same thing. And they always choose consistency over availability. On the other hand, you have the availability over consistency systems, the AP systems, are also frequently named as eventual consistency systems because the consistency will be there at some point if in the future all partitions are resolved again. However, to reach that eventual consistency, we need to fix the inconsistent states when nodes in different partitions are joining back together. And this can be really painful and error-prone and difficult to do right, especially since, for instance, a partition might happen in the middle of an upgrade, where you also have to think about, okay, but I have a newer version of my data structure and an older version, and now these need to be reconcilable as well. There's one thing that really helps to make this a little bit easier, and that is by using conflict-free replicated data types as our data structures, because these, from the get-go, state are written in such a way mathematically that they will always be able to be reconciled with any other version of the same data type. The main drawback of using CRDTs is that you are restricted to only using certain types of data types. And if you want to use something else, you have to resort on other mechanisms, usually last right wins, where one of the different possibilities wins over the others. And what last means here is a bit of a relative term. In practice, to make this even more complicated, usually we don't really like to make this choice once for a complete application, but rather per data type or maybe even per part of the data type. However, most tools out there either pick the one or the other, and usually don't allow you to configure this. There are some exceptions though, nicely, and hopefully this is something that will also be improved in the future. One other thing to think about, by the way, is that if there's no partition currently, there's another trade-off you can make between consistency and introducing caching layers to reduce latency, which might again introduce consistency problems. And this is given by the slightly more extended version of the CAP theorem known as PAC-ELK, if you'd like to look that up. One other thing I want to quickly mention, that if you have a lot of data and you need to scale, then there's another approach you can take which makes it a lot easier, because this is not actually a distributed system. If you're able to identify some parts of your data, some chunks that have no relation with other chunks of data, then you can work with each of these chunks on a completely separate server, and these never have to communicate. So this is wonderful for scaling, but it does not solve the problem of fault tolerancy, because each of these servers, when failing, will not be able to handle, your system as a whole will not be able to handle any requests to that data chunk. So that's enough about the general introduction to distributed systems. Now for the tools that we have available to us in Elixir and Erlang. What is really nice is that we already have some very good tools built in. We can start a cluster of Erlang nodes or Elixir nodes that are able to communicate together just by configuring them with the same cookie. And there are some other libraries that allow nodes to very easily find each other on the network as well, most notably libcluster. And the nice thing is that once you have such a cluster of multiple nodes, then sending a message from a process on one computer to a process on a different computer works exactly the same way as you used to within your original one computer system. So this is really nice, because we can now reuse all of our existing tools. If you want to make this even faster, then there's Partisan, which is another way for your nodes to communicate between one another, which is also nice to check out if you want. Now, if you're working with ephemeral data in your application, then Phoenix Presence helps you by sharing this information between your different nodes. And if Phoenix Presence is not exactly the right match to what exactly you are trying to do, then because it is built on a more general API Phoenix tracker, you can also, of course, work with that. And under the hood, it uses CRDTs, which means, again, that in this case, you don't have to care about exactly how your data types are resolved, because it's able to do that automatically for you. Now, if you dig all the way down to the most basic functionality that enables different distributed libraries, so for instance, usually you won't call these directly, but if you try to write your own distributed tool, you might encounter them. There are the functions multi-call and abcast that exist on the Gen server module. And these allow you to call all processes on all different nodes, or only on a list of some of them, that listen to the same name. And in this way, you can broadcast information to all the nodes so they are also aware of it. And multi-call collects all the different results, as well as all nodes that didn't properly respond. And abcast only sends the message and does not care about any results. So finally, you can also use hot upgrades, which are great to reduce fault tolerancy, but take more effort to get right. And on the other hand, if you are running a cluster with multiple nodes, then you could also just opt for restarting each of your nodes individually to the new version and having the others handle the new things as well. So hot code upgrades help with improving fault tolerancy, but not necessarily for distribution. One other thing I would like to mention is some of the lessons we learned the hard way at Planga, which is that your application should not necessarily be responsible for your database. So when we started out writing Planga, we were not entirely sure what kind of data storage we wanted to use. So we thought at first, okay, what should we choose? And then we decided, let's use Mnesia, because it's built into Erlang, so it's available everywhere, and there's no mismatch between the data in our Elixir application and the data in the database. And it's also distributed, so it should work well for our use case. However, this means that our application nodes are restricted to scaling only in, or application as a whole is restricted to only scale in one way, adding more application nodes. And this is great if you need more sockets because you have more active users. However, if you want to store more data in your database, you would like to add more disk space or more RAM to it. But Mnesia doesn't really work that way, and you don't want to add new application nodes to do this. And also, if you have your data in such a distributed database and there's a traffic spike, you would want to add more application nodes to handle this traffic spike. But after the spike has passed, you want to stop all these extra nodes that you no longer need. but now there's data in there as well. So that is not nice. So it would be better that to separate them so you can scale your application nodes separately from your database nodes. And this is something that unfortunately we only figured out later during the development process. So the next thing we did is look at different types of databases. And we decided early on that we wanted to use an eventual consistency style database and not a consistent transactional database, for the simple reason that AP systems are able to handle more data and have more throughput and are longer scalable than CP systems. So we looked at 4 different commonly used databases: Wijnja, Cassandra, CouchDB, and React. And all of them have great front pages and documentation that is filled with marketing speak, where they tell you that they are the absolute solution for every problem you will ever encounter, which is, of course, not the whole truth. So hopefully the things we figured out about them might help you as well. So let's start with Wijnja. It's really nice because it's Erlang's built-in database. However, it has a bit of a do-it-yourself approach. It does not, from the out of the box, handle the cases of partitions for you. You have to configure this properly yourself with relation to how your application would require it. And this is really difficult to get right. And I've seen a couple of Wijnja applications that use Wijnja in the wild that actually have not even thought about this. And these applications will at some point inadvertently crash and need some manual fixes, which are really difficult if you have a lot of data. Another thing is that if you get more and more data, then it can no longer be stored in a single table in Wijnja. So you wanted to cluster or distribute your data in multiple tables, which is possible. Wijnja has a hook for it, but you have to implement it yourself. And finally, Wijnja runs inside your existing node cluster, Erlang cluster, or Elixir cluster, which, as explained before, might not be the best approach. Next, we looked at Cassandra. Cassandra is used in practice in a couple of larger Elixir chat-related applications, amongst them Discord. Cassandra is a Java-based database, and it uses a column-based structuring, which means that if you have a user structure and someone updates the name and the email, and another person updates the email and the age of the user, then the name, email, and age of the user in there are updated separately. And which one of these 2 emails wins? Well, that depends on how precise the clocks of your computers are synchronized, which is a bit of a problem. Cassandra is not configurable in this regard. It always uses last write wins to choose which one to pick, and your clocks need to be properly synchronized for this to work well. And this is not really nice. However, it has great querying capabilities that are very similar to what you're used to from SQL databases. Then we looked at CouchDB. CouchDB is also built in Erlang, and it is a document store. So you can store JSON-like structures once at a whole. So if someone takes a user, which is email, and changes from that user the email and the name, and another takes the user and changes the email and the age, then only one of these 2 changes as a whole will be committed in the next version. And it uses JSON for querying, and it uses vector clocks for synchronization, which are a lot better than timestamp-based synchronization, because you don't have to synchronize the clocks of your computers completely to do this. However, if conflicts occur, then CouchDB will just pick one of the versions at random that wins. And this is not really nice. While it will pick the same version on each of your nodes, still you would like these conflicting versions to be reconciled with the current winner that CouchDB picked. But to do this, you have to do it yourself. So either you have a process running in the background, going over everything in your database, looking for conflicts that might have occurred, or when you query something, and you get the result back from CouchDB, you first have to look, hey, is there a conflict here? If so, update it in the database and query again before continuing on, which is also not the most ideal way to work with this. However, CouchDB is used in practice quite a lot and is also a nice and performant option. And finally, we've looked at React, and React is also Erlang-based. And it is a key value store, which means that it basically stores strings under keys. But instead of that, starting with React 2.0, you can also store CRDTs in there, which are, again, could be seen as Elixir maps. While React has more limited querying capabilities than the other solutions we've looked at, either having the ability to query on the primary key based on a range, or you have a more full-featured querying solution known as Solar, which, however, takes a second to find new updates because it lags a bit behind because the indexes need to be recalculated after storing something. Which means that you cannot use Solar for things that you want to return right away if you just save something and you want to return it elsewhere. So, still, the nice thing about React is that you are able to use CRDTs in the database, and React will itself solve the conflicts for you. So that is nice because now your application does not need to worry about this. And this is why we decided for Planga that it might be a good idea to use React for our application. Now, React used to be maintained by Basho, but it, at some point, the company closed. And then if React would be maintained was a big unresolved question. But now there are a couple of other companies, amongst them Bet365, that is picking up React development, and also everything is open source. And there are a couple of people working on it very diligently. And it is now slowly picking up speed again and getting a larger following. Now, regardless of what you actually decide to choose, using an AP-style distributed database is difficult because they work very differently from traditional SQL-like databases. And this makes it more difficult to move to them because much of the knowledge that many developers have about SQL-like databases no longer apply. And in general, they are more difficult to query and to perform arbitrary queries with. And usually you are more restricted in what way you can inspect all data and iterate over it. And one final problem that we faced, which made our development time significantly longer, is that there are no mature Elixir adapter for any of the 4 things we've shown you so far. This is one of the reasons why we at Planga are currently working on an Ecto 3 adapter for React. So we've decided to choose an eventual consistent database. We decided to use React and built our own React Ecto 3 adapter to make it also easier for other people in the future to use React with their Elixir structs. One other concept that we are using in our application to make it easier and easier to query mostly is the concept Snowflakes, which were first introduced by someone at Twitter, I believe in 2012, which is the idea that rather than having an ID which is incrementing by 1 every time you store something, or having a UUID, which is basically a complete random number every time, a Snowflake first takes the timestamp and then number representing the current node of one of the nodes in your cluster, and finally a random number. And then still you can generate 10,000 new IDs every millisecond. But in general, because your clocks are somewhat synchronized, all the IDs that are generated across your cluster will have sort of a temporal ordering, which is nice, especially in things like chatting applications, where you would like your chat messages to show up in the order that they were sent at. So this is where we are currently with our Planga application. And currently in production, this is still what is running. We run it on one node using Amnesia as the database inside of it. And users, when they connect with our front end that is written in Elm, they use the Phoenix channels, and behind the scenes, Phoenix pubs up to connect the different user-specific channels to each other in the different chat channels. However, in the next couple of weeks, and if you'd like a better estimation, I can estimate that in the next 2 weeks, after 2 weeks, I will be able to give you a better estimate. We are moving forward to running Planga on multiple nodes, and having a separate cluster of database nodes. And we are going to use React as a database and starting to use Phoenix Presence for ephemeral state, like what users are currently online. And we would like to improve the front end a little bit as well, so it is able to pick the node, the application node that is currently the fastest, and also switch when one of them is currently not responding. In the bit further future, we are looking into some of the other things we might be able to do, also depending on how fast we need to be in practice actually, such as adding Nebulux as a caching if calling into React every time is not fast enough, and it might also lower the memory requirements required for our application. And try out how viable it is to run nodes in different physical regions that still communicate with one another in the same Erlang cluster. And we would also like to expand on our front-end application so it works more properly, even if at some point a user is offline on their device because internet connections are spotty, so that they're able to reconnect properly. So what I would like to close off with is writing a distributed application properly is really difficult. However, Elixir and Erlang make it somewhat more bearable by having some great tools to help you. And tooling, especially for these smaller clusters, is there, but it is even being improved even further. And I would hope that some of you might be able to dive into this as well. So some projects to be aware of. Partisan that I mentioned before, which is able to connect your Erlang nodes in possibly a more efficient way. And LASP, which is a way of running computations in a distributed way, which is still in the beta state, I believe. Then Phoenix PubSub and FireNest, which the ideas from FireNest are now being integrated in Phoenix PubSub, which allow you to perform process discovery across multiple nodes. And libcluster, as mentioned before, to make it easier for your nodes to connect to one another. And of course, it would also be wonderful if you could check out the React Actor adapter that we're working on. I would like to thank Martin Wijnja, which is one of the guys of the React users group, which really helped us with many of the React questions that we were having, starting to run it. And also the Acto team, because at first I thought that implementing an Acto adapter would be a really daunting task, but it turns out to be remarkably easy and easy to get into. And finally, I would like the Elixir community as a whole, because you are absolutely amazing people to work with and communicate with and just be with every day on the Elixir Forum. So thank you very much. Please look at Planga, try it out. And we also, the source code is available on GitHub and you can try running it yourself. And we would love to hear any criticism about the code or any other ideas about running it. And with that, I want to thank you as well for your time listening to me today.
And thank you as well. It's nice to see some distribution going on there. So is there anybody with a question about this? Here we go.
Thank you very much for your talk. It was very, very interesting. I have a question about CRDTs and how the way you use them. Mm-hmm. So do you have any specific patterns that you have already identified that where some specific CRDTs fit greatly some specific situation, for example?
Well, usually, very often when dealing with data, we work with Elixir structs. And these can be mapped most of the time to React's map CRDT. The problem there, however, is that the fields that you store inside this map are usually strings or numbers or data similar to that. And these have to decide upon then again, okay, one of the two will win, with the last right wins. And but this is where however, there are some other types of structures when we're aggregating results, for instance, or counting views, where we can use some of the other CRDTs, such as the counter one, which aggregates the results rather than only picking one of the two as winners. And also, you have a set data type which can be used to aggregate many values rather than only picking one. So it really depends on what you're trying to abstract in your application, what you're trying to represent with your model.
Just to add a detail. And do you fully replicate the CRDT states, or do you use something like delta states where you only partially merge the mutations?
We're using React CRDTs, which I believe usually use delta CRDTs to reduce the communication that is going on between nodes.
Thank you very much.
All right. Anybody else over here?
Hi, thanks for the... Okay. So first, what have you used, how did you use Wijnja in your previous version of your software? And did you had any adapters or just the API which is provided by Erlang? And the second question would be, why you actually migrated from Wijnja into React? Because Wijnja will be always baked into the Erlang VM, and React is like a... React development is actually questionable in a way, you know.
Well, okay, so to answer your first question first, there is an Ecto adapter for Wijnja. However, it has some flaws. It only supports Ecto 2, and there are many features that are not completely supported. So we have a lot of extra fixes in the code to ensure that we can load the data properly. And so that's the answer to the first question. We're using an Ecto adapter from Wijnja, but it is far from perfect. And to answer your second question, as I explained, Wijnja runs in your same cluster, which is a disadvantage if you want to scale in multiple different ways. And this is the main reason why we wanted to stop using Wijnja, and also because we would have to handle the distribution parts, like the reconciling partitions ourselves. And yes, the other options using Cassandra, using CouchDB, are also great and probably very viable ones, but we really like the idea of working with CRDTs. And React development is, last I saw, like in February, a new release candidate for React 2.9 was released. So development is still going on, and I believe it's picking up again. Thank you. Any more questions?
Maybe we have time for one more. So, well, I actually have one. So the bulk of your data is probably these chat messages, right?
Correct.
So, but those can be sharded pretty easily. So
yes.
So why don't you just take the pragmatic solution?
The pragmatic solution to shard everything.
Yeah, like the conversations.
Well, we are thinking about in the future possibly sharding like the groups of conversations that all relate to a certain user application, say a web shop. However, while we would get more scalable, we would lose the fault tolerance aspect unless we would shard and then run each of these shards again on a smaller cluster. So that's why we're not doing that right now, because we think that the fault tolerance part is more important to get right first before the scalability part.
All right. Thank you. Well, give him one more round of applause. Wiebe Marten.
Thank you very much.